Okay, so welcome everyone to my talk on neutrinos and other light relics in cosmology. Now, as you can gather already from the first page, most of what I'll talk about is neutrinos, but I should remind you that we'll see that as we go along, many of these things apply to other light particles, such as axions, for example. And in fact, the only thing that typically really matters for this type of relic is that it's relativistic when it freezes out in the early universe. So that would be neutrinos, but also many other types of hypothetical light relics. But first, let's start with neutrinos. One of the main reasons, of course, we are interested in neutrinos in cosmology is from a particle physics point of view. It's because neutrinos are very, very hard to measure in the laboratory. And cosmology actually is one of our best tools for probing at least some neutrino properties. Of course, we already know that they are not massless. We know they do have masses. They are much smaller than other fermions in the standard model. We know they have no electric or strong charge. They do have weak charge. And of course, one other very important thing we know is that three charge current eigenstates, the flavor eigenstates, are related but not identical to mass eigenstates, which we usually call nu1, nu2, and nu3. And that leads to the phenomenon of neutrino oscillations. And of course, neutrino oscillations really is our main experimental probe of neutrino physics. Unfortunately, parameters like the absolute value of the neutrino mass, you cannot access using oscillation data. And that means you require something else. And that's typically where cosmology comes in. Now, before we go on, let's just remind ourselves what we do know about neutrino oscillations. We know that it's described by the three Euler angles of three-dimensional rotation, plus an additional CP phase that we are currently very close to having pinned down. And then if neutrinos are Majorana particles, we know that there are possibly two additional complex phases that have no implications for oscillation physics, but which are important potentially for neutrinoless double beta decay. So historically, these different angles were measured using different types of experiments. So for example, so-called 2-3 angle was historically measured in atmospheric neutrinos and since confirmed in long baseline data. Then the newcomer in terms of oscillation mixing angles is the 1-3 angles, which has been measured using reactor neutrinos and also now confirmed using other experiments. Finally, there's the 1-2 angle, which is in fact the oldest experimentally that was already basically seen for the first time in solar neutrino data way back in the 60s. And of course, since confirmed, for example, in the Camland reactor neutrino experiment. The final block here in the mixing matrix, we have not yet measured. In fact, we don't even know if it's there or this is just the identity matrix. The day we measure neutrinoless double beta decay, we know that this matrix is relevant, and of course we'll then also know that neutrinos are Majorana particles. Now, of course, like I said before, many of these parameters are experimentally very well measured. Like some of the mass differences are at least numerically well measured. But you notice here, for example, there's the sign ambiguity for the 2-3 mass difference, because up to this point, for example, atmospheric neutrino oscillations really vacuum oscillations, and that means that they are insensitive to the sign of the mass difference. Other parameters, we do know the sign of, for example, the 1-2 mass difference down here, which was measured using solar neutrino data. And the reason for that is that it's really a matter effect. So it depends strongly on the sun containing electrons and not many positrons. Now, from a cosmologist's point of view, really what we're interested in many respects, is the absolute mass scale. And the reason is that that's the parameter that actually influences cosmological structure formation and background evolution, whereas the flavor structure of neutrinos is not really important for structure formation. It is relevant, at least to some extent, if you look at Big Bang nucleosynthesis. Now, if we look at masses, we can structure neutrinos in two different schemes, one called the normal hierarchy and one called the inverted hierarchy. You see here at the normal hierarchy, we have the lightest being nu1, and then nu2 and nu3. The reason it's called normal, of course, is just that this is equivalent to what you have for other fermions in the standard model. On the other hand, you could also flip the sign between nu2 and nu3, and then you would have two heavy states up here, one very light state on here. Now, this is as far as you can go, basically, using oscillation data. The problem is that you don't know the normalization scale here. You can basically flip or switch up or down this m0 parameter. And in fact, m0 could be much larger, at least in principle, than the mass differences, in which case neutrino masses would be what is known as degenerate. It could also, of course, be zero, in which case you'd have strongly hierarchical neutrino masses. And the problem is that oscillation data really are only sensitive to mass differences, because we're looking at neutrinos in the ultra-relativistic regime, not in the non-relativistic regime. So in order to get at this m0 parameter, you have to turn to some other way of measuring, and typically one that's related to some type of kinematical probe of neutrino masses. And historically, the most important tool in that regard has been nuclear beta decay, because the neutrino mass enters, and if you look at the Curie plot of the electron distribution, you can actually tell whether the neutrino is massless or not, because you change the shape of that plot. We'll see that in a minute. Cosmology is also, in that sense, a kinematical probe of neutrino mass. So in cosmology, we mainly probe the contribution of neutrinos to the stress energy tensor. And that contribution depends quite strongly, actually, on the neutrino mass. And that's why cosmology is such a good laboratory for probing neutrino masses. And of course, also masses of other light relics. Finally, it's possible that you could measure, in some way at least, the absolute neutrino mass using neutrinoless double beta decay, because for neutrinoless double beta decay, you require a spin flip internally, so that you essentially flip a neutrino to being an anti-neutrino and reabsorb it. And that amplitude depends on the effective neutrino mass. Now, as I said to a cosmologist, things are very simple, right? So what we're interested in is really the total contribution of neutrinos to the stress energy tensor. And that can be easily parameterized in terms of this parameter called the sum of neutrino masses. So it's essentially just, in the standard model at least, m1 plus m2 plus m3, nothing more. And we can parameterize that in terms of the lightest neutrino mass to give us this plot here. So for the normal hierarchy, m1 is the lightest, and then you have m2, which is slightly heavier, and m3, which is somewhat heavier. And that gives us this end here. And for the inverted hierarchy, where you have two massive states and one light state, you can never go much below 0.1 electron volt. And that's already constrained from oscillation data, in the sense that we know there's a mass difference corresponding to something like 0.05 electron volts. And that means you need to have two neutrinos in that mass range. That leaves you up here. Now you can see, as you switch, as you turn the lightest neutrino mass upwards, everything is squeezed together, and essentially all the mass states are identical, and we're into what is known as the degenerate limit. And as you'll see later in the talk, right now, the bound on mass is roughly where the green line is, so to speak. And that means we're almost at the point where we can start to probe hierarchical neutrino masses. Not quite yet, but we're getting there. Now, just before we move on with cosmology, let me just remind you how you can probe the neutrino mass in other ways. So as I said, neutrino masses can be probed probed using nuclear beta decay. Basically, it happens right out here at the end of the Curie plot, where you can tell the difference, because if you have a massive neutrino, you need to set aside basically energy amounting to that mass, and that energy has to be taken away from the outgoing electron, which is really what you measure. And that means you can now see a difference right here at the very tip of the Curie plot. Of course, this is a very difficult thing to measure. Nevertheless, this has been done historically. And up to last year, our best bound was from the old Minds Neutrino experiment, which had a bound on the so-called effective electron neutrino mass, which is really just a sum of neutrino mass states, given like this. So it's an incoherent sum. It should be less than about 2 electron volts. And if you convert that to a sum of neutrino masses, you get to about 7 electron volts. Now, it has been improved quite tremendously. And that has happened because now we have online the Katrin experiment, which is the successor. It's based on the same technology as the old Minds Neutrinos experiments, but scaled up by orders of magnitude. So this is from the first data release in 2019, and you see the bound has been squeezed down by about a factor of 2, which brings you down to a sum of neutrino masses in the 3 electron volts range. And this will be improved by another factor of somewhere between 5 and 10 in the years to come. So really that is quite astonishing. Unfortunately, this is also in many ways the end of the line, at least for that kind of technology. It's hard to push it further. And that means that this type of experiment can never really probe into the hierarchical range of neutrino masses, unfortunately, which is maybe where we think we should be looking for neutrino masses. So that's where cosmology comes in. And why is cosmology sensitive to the neutrino mass? Well, basically, neutrinos are a source of dark matter. It's a different type of dark matter compared to ordinary cold dark matter, but it's still a dark matter species. And the same is true for other light weakly interacting particles. So basically, if we go and look at neutrinos, the effective neutrino temperature can be calculated quite precisely because we know standard model interactions quite well. We know that it's roughly given by this relation with photon temperature. That means that the current temperature of neutrinos is about 2 Kelvin. Now, that means we also know the number density of neutrinos. That means that we can convert that number density into the contribution to omega, given that we know the neutrino mass. So that's essentially the only unknown parameter in this equation here. Once we know the neutrino mass, we know the contribution to omega. And historically, of course, this was the first realistic, so to speak, candidate for dark matter. And you can actually get at omega h squared of about 0.1, which of course is what is required if you had a sum of neutrino masses in the range of 10 electron volts or so. We already know from experiments that's not the case, but more importantly, from a cosmological perspective, we also know that neutrinos, even though it's a dark matter candidate, behaves very, very differently from cold dark matter. And that's because neutrinos decouple while they're still very relativistic. They move at the speed of light until very late in the evolution of the universe. And that means that neutrinos have this tremendous free stream length, which is of order a gigaparsec for a 1 electron volt neutrino mass in co-moving units. And that essentially means that you suppress structure formation on all scales up to this free streaming scale. And you can see this illustrated here in 2 different simulations, one with massive neutrinos, one without. Sum of neutrino masses in this simulation was chosen to be compatible with the Minds bound. And what you see is that if you have massive neutrinos, you essentially erase all small scale structure. So I should note you that this simulation was set up such that total matter density is identical. So basically you take away cold dark matter and replace it with massive neutrinos. And that leads to a very, very strong suppression of structure formation on small scales. On large scales, it's basically the same density field. But of course, this would be highly disallowed by observations. And that means that you can actually probe neutrino masses using cosmological structure formation data. And that's a big area of research in cosmology and has been for decades by now. So we need to look at what the cosmological data, what kind of data do we have available. Of course, there'll be many other talks about this. We have the CMB data, temperature and polarization. We will have large-scale structure surveys of various kinds. Of course, this is a very old plot of the 2DF survey. It's just for illustration. We usually convert that, as for the CMB, into an effective power spectrum. There are many, many ways in which you can compress this data. But the only thing I really want you to take away from this particular plot, and this is the old one by now, is that we can actually probe the matter power spectrum at percent level precision in this K range here. And that means that you would be able to tell, at least in principle, a change in matter power spectrum at this level if it's caused by neutrinos. This is just another example. And you can here see exactly what a neutrino mass does to the matter power spectrum. So this is really what you should be comparing to the figure that I showed you before. So this is the ratio of matter power in a model with neutrino mass to one without neutrino mass. And as I said, and what you could see in this animation, is that the large-scale structure is essentially unchanged if you leave the total matter density unchanged. However, on scales below the free streaming scale, you can also see that power is highly suppressed. So if we had a 1 electron volt sum of neutrino masses, you actually suppress power by a factor of 2 or so, which would be very, very clearly visible. Now, even if we had a sum of neutrino masses in the 0.1 electron volt range, you would have a very strong suppression compared to what you see in the observational precision, right? It's many percent that you would suppress power. And therefore, you think that that should be visible. Unfortunately, of course, as we know, that's not how things work. There are many parameter degeneracies that you need to take into account. It's not only a neutrino mass that can change the matter power spectrum. Many other parameters can do the same thing, although not in exactly the same way. And that means that the neutrino mass is degenerate with a number of other cosmological parameters, which makes it somewhat harder to measure. Now, if we go back to neutrino physics, we take all this data, we run our Markov chain Monte Carlo, then we can have a look at what kind of mass constraints do you actually get. And this is from the 2018 Planck release. You can see here that the sum of neutrino masses is with CMB constrained to be less than 0.2 something electron volts, which of course is much, much, much better, formally at least, than what you can measure using the Katrin experiment. Of course, I should also remind you here, what we're really measuring is the energy density in some hot dark matter component. We're not measuring the neutrinos directly, as opposed to, for example, beta decay experiments in which you have much more direct access to the physics that makes the neutrino. And that makes the bound somewhat different qualitatively. Of course, it's not really on the same footing. Now, if we add AO, for example, we much improve the bound and we squeeze it down to 0.1 electron volt range. And there are many, many other types of such data analysis in literature. This is from another one that I did with one of my collaborators last year. And what you see is, again, the same thing. The sum of neutrino masses is constrained to be of order 0.1 electron volts. Of course, it depends on the data sets that you use and also the parameters that you use in the analysis. That is something that I'll discuss a little bit more in a minute. One could also, of course, ask the question, can we tell the difference at the moment between the normal and the inverted hierarchy using cosmology alone? And really the answer is no, because the sum of neutrino masses is constrained at 95% confidence to be less than about 0.1 to 0.12 electron volts. But that's still compatible with both the normal and the inverted hierarchy. And really at the moment, the precision is not sufficient for us to tell the difference between these two hierarchies, unfortunately. That might change in the future, of course, but at the moment, we really can't tell the difference. Another thing I should caution, of course, is that, okay, there are many other things that you can look at, but let's just skip on to the next slide, which of course is an important cautionary slide, so to speak, namely that when we do cosmological parameter estimation, we have to choose a model which is not all that well defined. Of course, we can think that minimal lambda CDM is a very well defined model, yet we don't know what the dark matter is, and we don't know what the dark energy is. We can assume that it's a cosmological constant. We could add other types of dark energy. We could add other types of light species. We could add to the complexity of the model space. And if we take a given data set and we run our parameter estimation, of course, we'll get looser and looser constraints the more complex the model gets. On the other hand, we could also use many, many different types of data sets and pile them one on top of the other, and then we'll typically get stronger constraints. We might even get a positive detection, but the problem here really is that if we do that, if we play that game, then the bound becomes very unrobust. It becomes very fragile because many of these data sets might be susceptible to unknown systematics. And historically, of course, we've seen many, many cases of claims of neutrino mass detections, and they all went away in the end because of unknown systematics that affected the given data set. On the other hand, we could also be overly pessimistic and only use the best understood data and a very complex model, in which case we get a very loose constraint, and it will take forever basically to get anywhere. It might be very solid, but it won't really be all that competitive. And of course, the middle road, as so many other times, is probably the best way to go. And right now, that leads to this constraint in the, say, maybe 0.1 to 0.3 electron volts range. Now, of course, there are always ways to get around such a mass bound. You can change cosmology in various ways. Like I said before, you can fiddle around with cosmology, you can change the dark energy behavior and so on. You might couple, for example, neutrinos and dark energy. You could also think of modifications to neutrino physics, which from a particle physics point, of course, is a very interesting possibility. You could make neutrinos strongly self-interacting. You could have models in which the neutrino mass is an emergent feature. For example, there's the model of Dwali and Funke, where they have basically a late-time neutrino mass generation. You could have mass-varying neutrinos, which is essentially a form of dark energy, a scalar field coupling to neutrinos and generating the mass term through that method. And in all of these cases, you can basically avoid the suppression of large-scale structures. So there are various ways, of course, to circumvent the bounds. And that's also one of the reasons why direct experiments can and will remain important. Now, one example, which historically has been discussed quite a lot, is the degeneracy between neutrino mass and the dark energy equation of state. This is just one amongst many examples of such studies. You can see if you take the CMB data and you add an equation of state which is different from -1, you do get this degeneracy, and that means you can allow for somewhat higher neutrino masses. The degeneracy is not as strong as it used to be because of course cosmological data keeps improving, and that tends to break these parameter degeneracies. Now, another interesting question you might ask is, are there any other neutrino parameters that can be probed using cosmology apart from the mass? And the answer is yes. So one other parameter, of course, that is important is the number density of neutrinos, or you can also think of this as the effective neutrino temperature. So that would affect both the number density, but also the energy density at high temperature. In the standard model, we think we know this number quite precisely because we know the neutrino temperature, or at least we think we know it. On the other hand, it could also be changed due to a number of different effects. It could be even very late reheating after inflation, for example, can change this number, because you might be in a situation where you cannot completely thermalize neutrinos prior to them freezing out. So there are many, many different possibilities for that. And really, you can also think of this parameter as something that should be measured, not assumed to have some prior value. And that historically has also been done using a number of different cosmological tools. If you go back in time, Big Bang nucleosynthesis was historically the most important probe of this number. But nowadays, the CMB is also a very powerful probe, and actually by now more precise. So the way it's done is typically you define the so-called effective number of neutrino species, which is the total high energy or high temperature energy density in neutrinos divided by some normalization that we call rho nu naught, which is defined like this. So this is very close but not identical to the standard model neutrino energy density. There's a slight subtle difference between this and the actual density. We'll see that in a minute. You can think of this an effective parameter as a measure of all dark radiation in the universe. So that can be, of course, neutrinos, but it could also be other types of very light relics. So in any case, even if neutrino physics is completely standard model, it's still an important parameter because it accesses very early decoupling, very light particles that might be of interest. Now, from the Planck 2018 data analysis, again, you see that this number is very close to 3. It's standard model prediction, like I said before, is not exactly 3, it's 3.046 roughly, because neutrinos are not completely decoupled by the time that electrons and positrons annihilate in the early universe. So some small amount of entropy is transferred from electrons and positrons into neutrinos. And there are also finite temperature QED effects at play. And altogether, you get this standard model prediction of 3.046. Now, the data seems to indicate that standard model prediction is right in the middle of what you infer from cosmological data. So as of now, it seems there's no real evidence for any kind of non-standard light relics around. That again can change in the future. We'll have much more precise information about this parameter also with future data. So summing up cosmology and standard model neutrinos, there's no evidence for any kind of non-standard physics. We only have an upper bound on the neutrino mass, which is not perhaps all that surprising, because given our knowledge of neutrino oscillations, we might think that perhaps the sum of neutrino masses should be in the 0.05 to 0.1 electron volt range, which we can't really access at the moment. However, if you look at neutrino physics, there are also hints of interesting beyond the standard model physics. So there are various neutrino oscillation anomalies. There always are and probably always will be, because neutrinos are very difficult to measure experimentally. But at the moment, there are some hints of perhaps the existence of an electron volt sterile state, so one that is a singlet under the standard model interactions, but which could be thermalized in the early universe and contribute to the energy density. And such particles, of course, have also been constrained using cosmological data. This again is from the Planck data release paper. And you can see a parameter here called the effective sterile neutrino mass. That's basically the physical sterile neutrino mass multiplied by a factor that tells you that, well, sterile neutrinos are less abundant typically than normal neutrinos, and that has to be taken into account, and that basically gives you this effective mass parameter. Now, the bottom line of all these analyses is that sterile neutrinos in the electron volt range are not allowed by cosmology. They cannot be fully thermalized. In fact, they can be only very marginally thermalized in the early universe. And that's problematic because if you look at the kind of mixing angle that is required for the short baseline anomalies to be explained in oscillation data, such neutrinos would be fully thermalized through a combination of scattering and oscillation in the early universe, and that would be very highly at odds with cosmology, something like at the 5 to 6 sigma level. And the only way to avoid it is to invoke some kind of non-standard physics beyond just the existence of a sterile state. And there are various ways you can do this. You can have a non-zero lepton asymmetry. You can have these additional neutrinos charged under new interactions, and that can lead to a suppression of the thermalization of these particles. Let me just show you one example, but there are many in the literature. This is one particular model that we've been studying a bit over the years, one in which the additional neutrino is charged under a new pseudoscalar interaction with a very small coupling strength. Even this very small coupling strength actually leads to very, very interesting behavior. So first of all, it leads to a delay in the thermalization process, which suppresses the overall contribution to the energy density. Second, it means that this additional neutrino state doesn't really free stream in the normal way because it's strongly interacting. So in fact, it undergoes acoustic oscillations rather than just free streaming. And this has been studied a number of times in literature, and it goes too far to go into all the details. The only thing I wanted to point out here is that you can actually get something that fits the data extremely well. So for example, one thing that's of interest, like I said before, is that there's hardly any free streaming effect in this model. So first of all, of course, you do have these acoustic oscillations. Second, this new pseudoscalar is assumed to be very light, and that means that the massive neutrino actually has a new way of escaping. So basically, once it goes non-relativistic, it will start per-annihilating into these new pseudoscalars that are very light. And if you look at a sterile neutrino scenario in the electron volt range, with just normal sterile neutrinos, you see this well-known and very strong suppression, the matter power spectrum on small scales. However, in this particular interacting model, you have hardly any suppression at all. The reason, of course, is that you never get a very large contribution to the energy density from these sterile neutrinos because they're essentially gone by the time structure formation really gets going. And that leads to something that is much, much closer to the standard lambda CDM model in terms of the matter power spectrum. CMB's power spectrum is affected, but you can change other parameters so as to leave the final total CMB spectrum more or less unchanged. And intriguingly, and something that is perhaps worth taking note of, is that this particular model, the best fit Hubble parameter, is right in the range where it's measured to be by local observations. So it's something like 73 to 74, which of course doesn't mean the model is true, it's just an intriguing observation. Now, for the remainder of the talk, I will just look to the future a little bit and see what can we expect in the coming years in terms of constraints on neutrinos and other light relics. So this is from a very nice summary table that was produced actually a number of years ago by now. It's still quite nice to get a feel for what we'll see in the future in terms of sensitivity to these neutrino parameters, the sum of neutrino masses, and the effective number of neutrino species. And now it's measured actually in milli-electron volts, which sort of indicates to you that we're at the point where we can start to access hierarchical neutrinos. So right now, we're basically here in the 100 milli-electron volt range. If you look, for example, at various stage 4 CMB experiments, we can perhaps go down by a factor of 4 or so relative to current sensitivity, and that would lead us into the hierarchical neutrino range. You can also see that it's possible to measure this N effective quite precisely, actually. Now, if we look at something at other types of experiments. You could, for example, look at what Euclid and Planck will be able to do. It's also down in the tens of milli-electron volt range. You can see another parameter analysis forecast that we did a few years ago. And this is from basically Planck and projected Euclid data. You can see that if you add all the types of data that you get from a Euclid-like experiment, you can actually get to something like a sensitivity of 0.01 electron volts for the neutrino mass. And that would actually mean that you would have a real detection of a non-zero neutrino mass using this data at least something like the 5 sigma level, even if it's the normal hierarchy. Perhaps this is slightly optimistic, but I think it's fair to say that with data that's coming in within a decade, we will have a detection of a neutrino mass at something like the 3 to 5 sigma level from cosmology. So that's really going to be quite impressive. In terms of this effective number of neutrino species, you can also measure it very precisely. And I should also perhaps remind you that the standard model prediction here is 3.046, not 3.0. And the 0.046 comes from all these interesting effects around a temperature of 1 MeV in the early universe. And we'll probably get to the level where we can actually start to see these effects, not at high significance, but at least we will be able to see hints of them. And that means, for example, we'll be able to start probing finite temperature QED effects in the early universe. So that's actually quite impressive, I would say. Now, a question that I've often been asked, and I know many other people in neutrino cosmology have often been asked this question, is can we actually ever, even in the future, probe the neutrino mass hierarchy directly? And by that, I mean not just the sum of neutrino masses, but I mean really the hierarchical structure of the neutrino masses. And that question has been addressed a number of times in literature, but we went back and had a look at that earlier this year. And the answer really is that no, there's no way that even future cosmological data can really see the difference between the structure, between different types of neutrino hierarchies. What cosmology can and will measure is the contribution of neutrinos to the energy density, not the ordering of the mass states. So the only thing you really can say is that if we probe the neutrino mass sum to be less than about this range here, we can exclude the inverted hierarchy based on the fact that you cannot go much below 0.1 electron volt in the sum of neutrino masses. But that's an indirect statement. It's not a direct measurement of the mass hierarchy. And if the mass sum turns out to be larger than this value, then no cosmology cannot tell the difference between normal and inverted hierarchy. Of course, that's perhaps not extremely problematic because we know that we will, from oscillation data, be able to tell this difference. So it will be measured using other methods. But the conclusion from cosmology is that, yes, cosmology can extremely precisely probe the sum of neutrino masses, but not how these masses are distributed internally in the neutrino sector. That's not a possibility. And the very final thing that I just want to touch upon is actually what I have been spending most of my time on in recent years, and also many other people, is to understand in more detail how neutrinos affect structure formation, not in the linear perturbation theory regime, but in nonlinear structure formation. And that's something that will be important, for example, for understanding experimental data coming from Euclid and other future surveys. Now, if we want to really get the most out of these data sets, we should be able to control systematics, for example, for weak lensing measurements out here at high L at the percent level. That means understanding, for example, the matter power spectrum, or rather the clustering of matter at the same level of precision, even on small scales. And that's a very daunting task. It's extremely difficult. Of course, the main difficulty remains the baryonic component, star formation, supernova feedback, all these things that are still not completely understood. neutrinos are important, certainly at the percent level. We know that already from linear perturbation theory. And this is what we have been looking at. So let me just show you a very early example of such a calculation based on n-body simulations. It's more than a decade old. You see, for example, here the green lines, those are the predictions of matter power suppression, linear perturbation theory for different neutrino masses. And the colored lines here, those are predictions from n-body simulations. And you see universally that it's predicted there's a range here, but the suppression is somewhat higher. Then it also becomes smaller. In any case, there's a significant difference that you need to take into account. And as you can see, many other people have been working on this and are currently working on this. We're also incorporating these effects in some of the large Euclid runs that have been done. So for example, in the flagship 2 run, which is 4 times 10 to the 12 particles, it's very large. Massive neutrinos have been taken into account, and you can tell the difference. You can see another recent example here, which is the suppression for different values of the scale factor with and without massive neutrinos. You can see again it's the power spectrum ratio. This is now also fully compatible with general relativity. So even though it's a Newtonian n-body simulation, TR effects have been consistently taken into account, and that also makes a difference, which is borderline observable with surveys like Euclid. So just to sum up, this is ongoing work, and it seems to be under control at the required level of precision, but this is, again, still work in progress. So finally, conclusions. I think, and this I think has remained true for the past decade or more, neutrino physics is a really, really good example of how you can do very mundane, normal experimental particle physics using cosmology. So we're not talking about extremely high energy particle physics where you probe God scale physics or anything like that. It's a very simple particle physics question. What is the mass of standard model neutrinos? You can actually address that using cosmology. We also know that by now the mass bound on neutrinos is much stronger from cosmology than from direct experiments. But again, it's important to remember that this is a more model dependent bound. And in fact, even if we measure neutrino masses from cosmology, we can't really say if it's neutrinos or something else, just that there's the existence of a hot dark matter component with a non-zero mass. We also note that cosmological data, at the moment at least, shows no evidence for beyond standard model physics in the neutrino sector. And that means that if sterile neutrinos do exist and are experimentally confirmed, cosmology will have to find some way of incorporating them. And that would presumably require interesting kinds of non-standard cosmology or interesting kinds of non-standard neutrino physics. And finally, as I talked about in the last few minutes, future surveys will allow us to actually directly probe the contribution of neutrinos to the energy density and actually measure the neutrino mass. Okay, so that's the end of my talk. Thank you very much.